Okay, so divide and conquer. First of all, we have already used it to design a merge sort algorithm. It turns out to be a quite efficient way of implementing the sort algorithm. Okay, and if we have a brief review here, we know that there's three basic steps: divide, which is to decompose the original problem into smaller subproblems, and those subproblems has the important property that they are actually the same type of problem, which is only smaller in size. That is really important. Okay, so we shouldn't generate new types of problems. If the new types of problems cannot, because the new types of problems cannot be solved by the same algorithm, right? We are talking about using recursive solutions, because only if we have the same type of subproblems, then we can apply the algorithm recursively. And those recursive applications actually occur is the conquer step that we are referring to. Okay, in the conquer step, we are solving all the subproblems in a recursive style. And the last is to combine the solutions to obtain the solution to the original problem. Yeah, so that is the basic outline. Okay, it's so from a higher level, I think it's really clearly defined. Okay, so when we divide the problems, because the input has limited size, so we cannot divide them infinitely. Okay, so if it's the case, the subproblems are still divisible, or is still large enough to solve recursively, then we call this is the recursive case. Okay, but eventually we will hit some point that the inputs can no longer divide it. Okay, and that is the so-called the bottom case, or the base case for the dividing step, or it is the base case for the recursion. Okay, because we somehow need to provide some basic solutions to the simplest case of the problem. Okay, the recursion will never occurs infinitely. Otherwise, the algorithm will never return, right? So in this chapter, I think we're gonna primarily use the two types of problems as a showcase, as an example, to study the divide and conquer approach. The first one is called maximum subarray problem. The second one is called matrix multiplication problem. So we can, through these two examples, we will see how divide and conquer approaches can be powerful, and how it can be used to overcome the limits in basically non-divide and conquer approaches. Okay, so before we get started with the maximum subarray problem, let's warm up a little bit with the recurrence. So we know this term in merge sorts. It basically refers to the way that we describe the running time of divide and conquer algorithms. We use basically several equations in lines to describe, actually 2 lines of code to describe the base case, okay, which is the simplest inputs, the smallest subproblems. In this case, for merge sorts, this base case is n equals 1. And the recursive case in the second line is how we divide the problems and combine the solutions. Okay, so this 2 times n equals n over 2 means that we will have, after the dividing, we will have two subproblems, and each subproblem is half the size of the original one, okay? And this big theta of n, it is the cost for combining the solutions to the, by combining the solutions of the two subproblems, okay? But if we want to analyze in detail, we also need to analyze the cost for divide, right? The divide and the cost for combine, okay? But since it's in merge sorts, the cost for dividing is really irrelevant compared to the cost for combining. So anyway, we have this recurrence in two equations to describe the running time for merge sorts. And for basically all types of divide and conquer algorithms, we can use a recurrence to describe the running time. And it is not necessarily, the subproblems are not necessarily the same size. They can be unequal sizes because it's the way that we divide the subproblems that determine the size of the subproblems. So for example, we can choose to cut this input sequence at the 2/3, at the position of the 2/3 of the length, right? So that will result in the first subproblem of n 2/3 the length, and the second problem that is 1/3 the length. That is also, I mean, okay, right? We can choose to do that, though it doesn't necessarily give us any advantage, okay? And also, in the other cases, the subproblems, they are also not necessarily a constant fraction. So in some cases, we can get the subproblem by decrementing the size by 1 or by some other constants, constant amounts, okay, which are totally acceptable. So which also means that the form of recurrences can be really diverse. We can have all kinds, various types of, recurrence equations. It's not necessarily in the same form as the merge sorts. All right. So in terms of writing recurrence equations with a more convenient style, we can use some simplified techniques. Okay, so because technically the merge sort should, the recurrence of merge sort should be written this way. Okay, we should use the ceiling and the flooring, okay, because the inputs is not necessarily, the length of inputs is not necessarily in even number, right? So in order to handle those uncertainty in the input data, we need to consider all possible conditions, okay? But usually we can ignore the floors or the ceilings and the boundary conditions. And we can normally say that we can just use one equation to describe the recurrence, okay? Because these are the most take-home message we want to know, okay? All right. So the purpose of writing recurrence equations is that we want to solve them. Well, basically, we want to solve the recurrences in order to get some analytical solution to, for example, we hope to use some asymptotic notations to describe the running time, okay? So we basically, in this chapter, we will introduce several methods for solving recurrences. The first one is called substitution method. Okay, it basically, this method uses a guess. We will first guess a bound, guess a solution, and then we use mathematical, the technique of mathematical induction to prove our guess. The second type of function is recursion tree method. And this is the method we have we have shown in the merge sort example, which means we convert the recurrence into a tree structure, right? Remember, we wrote the root node C of n and do the splits. The first one is T of n over 2, right? The second branch is T of n over 2 in merge sorts. That's how we do the first tree structure in merge sorts. So this is typically the way that we use for recursion tree method. And we will keep the split going on until we reach the bottom level. And then we need to sum up all the nodes in the tree in order to get the ultimate solution. That's called recursion tree method. Okay, so these two methods are quite intuitive. Empirical methods. We based they are in practice. We will come across very different cases when two different inputs numbers. But for the third type of method, which is called master method or master theorem, and this is the general solution for recurrences that look like this form. Okay, so which means it is a more general solution, and we will know how to use it after the lecture, all the lectures for this chapter. Okay, so after we have know how to use master theorem, whenever we have a problem that looks like this, whenever we have an algorithm whose running time can be described in this form, a times t of n over b plus some form of function, we can apply this master method or master theorem to directly get the solution. Okay, there's no need to use the tree to draw the tree or to use substitution to get the proof. Okay. Anyway, so that is basically how we organize the outline for the remainder parts of this lecture. We will look at an example, use the maximum subarray problem to more systematically introduce the divide and conquer approach. Okay, yeah, let's look at the problem. Okay. So imagine you have some money to spend and you choose to invest in either in stock markets or in other markets. So you have the opportunity to invest, and you are allowed to buy 1 unit at one time and to sell it at a later time. Okay, and of course you want to buy low and sell at a higher price, right? And actually, in this scenario, we're kind of cheating here because we are allowed to learn all the future prices. So in order to introduce the problem, okay, we are given all information about future prices. Okay, and our goal is simply to buy low and sell high, and we want to maximize our profits. Okay, so that says we want to kind of buy in at the lowest points and try to sell out at the highest points. Okay. For example, if this is the price for the stock markets, or by you can imagine it as a price per share for a company. Okay, so from day 0 to day 16, we have the corresponding price here. It fluctuates. Okay, and we want to choose a day to buy in and choose a day at a later time. Okay, we can never go back to yesterday and sell it at the price of yesterday. So assume that's not doable. So we have to buy in at one day and sell it at the later days in order to get the maximum difference. Okay, so this is a quite practical problem, and let's analyze it a bit. So what would be a straightforward strategy? Okay, I think it's easy to say that to come up to the solution that we can buy in at the lowest point and sell at the highest point. Okay, so that means we should either find the lowest or the highest prices. Okay, and then we will work left from the highest price. Okay, because if we want to sell at the highest price, then we must buy in before it, right? Then that means we must work left from the highest price, and to find the lowest price, and that is the point that we buy in, right? And the other way is that we work on the right side of the lowest price, okay? And we want to find the highest later points, right? Because we choose to buy in at the later points, at the lowest price points, then we must sell it at a later stage, right? And then we need to compare these two ways indicated by these two colors, the blue color and the orange color, and we want to see which one gives us a better revenue, right? Better profits. Okay, so if we highlight it into these charts, then we can notice that there's a lowest point in day 7. Okay, then according to the first strategy, we need to buy in. So according to the second strategy, right? The second strategy says that, oops, if we choose to buy in at the lowest point, then we need to find the highest point to the right of it, right? So these two highlighted points are our solution according to this strategy, okay? And we need to compare this strategy with the strategy that we first choose to choose to sell at the highest points. Okay, so this is our highest point. And we must find the day to buy in, right? Which is 1 day before it. Okay, so we need to compare these two strategies to see which one gives us the better profits. And of course, in this example, we can see that the difference between the lowest points and the highest to the right of it is a better one. The gap is much bigger, right? The gap between the two red circles are much bigger than the two green circles. Okay, so we can actually buy in at day 7 and sell at day 11. That seems to be our best option here. Okay, so it may work here, but this strategy not always work. If, for example, when we have a global price like this, okay, so if we try to find the maximum point, it's in here, right? And the lower point is here, right? So according to the strategy described by these two ways, right? We should either buy in at the lowest or sell out at the highest. Then we need to buy in at day 0 and sell out at day 1, right? Because if we buy in at day 4, there's no sellout date, right? So, and of course, it gives us such a gap. And we notice that this is not the best option, because if we look at this one, the little peak here and the valley here, actually we can choose these segments, which will give us a better option, get a better profits, right? But the thing is that the peak here, it is not the global highest points, and the valley point here, it is not the globally lowest. So our strategy will not work in this case, right? So we got to consider a different way, okay? Which means that it is a harder problem than we thought, than we expected, okay? It's not that easy. It's not that simple problem. We shouldn't just consider the global highest or global lowest points. All right, so let's see what we can do here. Okay, so if that doesn't work, then it's actually so I see a suggestion that why can we look at all the pairs of lowest and highest and pick the one with the greatest difference? So that is, thanks for the comments. That is similar to the brute force solutions that I will show here in this example. Yeah, so why not just try every possible pair of buy and sell dates, right? Just pick up the just choose among all possible combinations, okay? So we can easily write this as an algorithm. For example, given the input array, and we assume that all the prices are stored in the input array A, and the starting day and the ending date are indicated by these low and high indices. Okay, so we can simply, for example, we use the max profits to store the profits, and we use the max left to store the left index that gives us the max profits, and the max right to store the right index that stores the max profits. Okay, so it's actually two nested for loops. And the first loop counter ranges from low to high -1, and the second loop counter j ranges from 1 to the right of I, which is starting from I+1 to high. Okay, so in this way, we use two nested for loops to iterate over all possible of pairs within this input array. Okay, and we should consider compute the profits by use the right end to minus the left end. Okay, and if that profit is greater than the existing max profits, then we will need to replace the existing values in these variables. And lastly, we need to return the maximum profits, right? Which is a very easy solution to think of, because we don't care about running time. We don't care about efficiency. So this is guaranteed to kind of give us a solution, right? So if we think of how much time it's going to cost us, it's also straightforward to compute, because if the input has n numbers, then basically the inner for loops will be executed for that many of times, right? The first inner loop will be executed for n-1 times, plus n-2 plus 1. And this is a summation of an arithmetic series, which gives us a quadratic running time solution, okay? And we can also think of it as a combination problem. We are taking two indices out of n possible values. So the combination of picking 2 from n is basically a quadratic function, okay? So we have a quadratic time solution if we use the brute force solution. And that's not bad, right? We are kind of happy because it gives us the solution, because we examine all possible values. There's no way to ignore any, to overlook any, right? But the thing is, it's a quadratic running time function. if we recall insert and sort, it is not the ideal one. It is some space for improvements. Okay, when an input is large, then a quadratic function will grows really fast. Will cost us a lot of time. So how do we do better? That is the problem we need to think about today and try to solve. Okay, so let's do this together step by step. So in order to, yeah, that's a good point. We actually need to divide it because it's divide and conquer approaches that we are talking about today. Okay, so if we do a little bit transformation first, okay, this will help us approach the optimal solution easier. Okay, so we can kind of rephrase the problem. Our goal is to find a sequence of days over which the net change from the first day to the last is maximum, right? We are actually considering the net change. So we can consider the daily change in price, okay? The change on day I is the price of today minus the price of yesterday, right? That's something we can easily compute given the input array, okay? So again, use this example. The first two rows are the same as the previous slide. It's just the price table. And we will add a new row called this change row, which records the amount of change from the current day to yesterday. So day one, the net change is 13. And for day two, the net change is -4 because 110 minus 113 is -4. Okay, that's how we compute this the change row. Okay, so now we use this change as input. Okay, and it will make us implementation for the more efficient algorithm much easier. Okay, so actually, if we treat the change row as our input now, actually what we are finding here is the non-empty and contiguous subarray of A, whose values have the largest summation, right? If the array over which we have the largest summation, then it means that the net change from that period is maximum. Okay, so this makes us a new problem, which is easier to handle basically, because we just need to sum up all the numbers in it. Okay, there's something we can maximize now. Okay, and we call this contiguous subarray to be the maximum subarray. Okay, so for example, in this case, the maximum subarray is from A8 to A11, which gives us the maximum sum to be 43. Okay, so how does this information help? So maybe at the first glance, it doesn't help because it's the same thing. If we want to find the maximum subarray, we actually need to check still that many of possible subarrays for a period of n days, right? If we follow the same thoughts, it's actually still a lot of work to do. It doesn't change the nature of the problem. Okay, so we basically need to take a different approach. Okay, let's try divide and conquer. Okay, rather than the brute and force way. So the thought is like this. In order to find a maximum subarray that is from index low to index high, we can actually divide it into two subarrays that is of equal size. Okay. For example, we can find the middle points. Right. Let me use a new index called mid and the mid plus 1. And here, mid is the midpoints. Okay. Then any subarray A of j, actually A from I to j. Okay, so this A from low to high is the complete input. Okay, and the subarray within A low to high is a subset of is a segment of A from low to high. So this subarray A from I to j must be exactly one of the 3 cases. The first case is that this subarray is entirely in the left, which is from low to mid, right? So that means the I and j are bounded by the low and mid. It is the subarray from I to j is entirely to the left. The second case is that it's entirely to the right, which is bounded by m mid is bounded by mid plus 1 and high, right? And there's a third case, which is the subarray I from I to j is actually crossing the midpoint. Okay, the I is between low and mid, and the j is between mid and high. Okay, that is the third case. Is there any other cases? Actually, no. Okay, actually, these 3 cases include all possible cases exhaustively, because there's no way that a subarray can lie into another case, right? Think of it. We find the midpoints, then any subarray of the total of the complete inputs must be one of the 3 cases, either left, either right, either crossing the midpoints, right? We're actually enumerating all possible cases here. All right, so how does this help us? Because we are listing all the 3 cases here. Then basically it means that the maximum subarray that we want to find must be one of the 3 cases. Okay, it must be within these 3 cases. Okay. All right, now let's consider the first 2 cases. If it's the 2 cases, the first 2 cases, either on the left or on the right, the entire subarray is within the left or within the right, then we can find the 2 maximum subarrays for the left segment and the right segment recursively. Okay, because they are the smaller instances of the original problem. Okay, remember the original problem is find the maximum subarray from low to high, but now we are simply divided into 2 subproblems, which is from low to mid and from mid plus 1 to high. But they are still the same problem, right? We want to find the maximum subarrays within left and within right, right? That's for the first 2 cases. But for the third case, if the subarray is crossing the crossing the midpoints, then it's a different one. Because the maximum subarray that cross the midpoints include the midpoints. It's no longer the same original case. It is no longer the same type of problem. Okay, so what we can do is to compare the solutions from the 3 cases and find the one that has the largest sum within the 3 cases, among the 3 cases. Okay, so this is a typical divide and conquer thoughts. And we have divide at the beginning here. We divide it into two sub arrays. Here, this is our divide. And here we conquer them. We conquer the two cases using recursive style, right? Because they are the smaller instances of the original problem. And we conquer the third case by implementing some algorithm to solve it. And finally, we take the larger one that has the highest summation, that has the maximum summation, which is the combined step. Okay. So we can guess that the heavy lift is actually here, right? The heavy lift is where we solve the third case, that when the subarray is cross the midpoint, how do we find the maximum subarray of it? Okay, so now let's proceed to the next slide and do the heavy lift. Okay. So if we describe the process we have shown in the previous slide, it's actually here. We find the midpoints, right? So in the first case, the subarray is entirely to the left. In the second case, it's entirely to the right. The third case is that the subarray crossed the midpoint. So if for any subarray that crosses the midpoint, it must be like this, right? The shadow area indicates the elements in the subarray, and we have the left and the right indices from I to J. Okay, so it must comprises two parts. For any subarray that crosses the midpoint, it must consist of two parts. The left part from I to mid, the right part from mid +1 to J. Okay, then we are actually trying to find the maximum subarray with the largest summation among three cases, right? The first case is from low to mid. Second case is from mid +1 to high, and the third one is from I to J. Okay, we are comparing these three parts, and we try to find the largest one. We're trying to find the subarray that has the largest summation among the three cases. So this slide is basically a visualization of the previous slide. And I think if you have difficulty understanding the whole process within a short amount of time, you can spend some time reading these two slides over when the lecture is done. Okay, so the heavy lift is here. The heavy lift is the third case. How do we solve this case? How do we find the maximum subarray for a subarray that crosses the midpoints? Okay, that's something we're gonna show in the next slide. All right, how do we find the maximum subarray crossing the midpoints? Now we have some constraints. It's no longer an unbounded question. It is a bounded question that we must satisfy this subarray crosses the midpoint, right? This is a constraint we need to keep in mind, okay? Because it is not a smaller instance of the original problem. The original problem doesn't have any constraint at all, right? Original problem just asked for the maximum subarray, but now it gives a constraint that it must cross the midpoint. Okay, so actually this.
Professor?
Yes.
Just a quick question. So when you say crosses the midpoint,
yeah.
It doesn't have to be the midpoint of the subarray, correct?
No, it's not the midpoint of the subarray. It's the midpoint of the original array.
Oh, okay, makes sense.
Yeah. The midpoint is where we compute from low and end, or from low and high. So low is the left point, so the high is the right point of the original problem. Okay, that's a good point, good question. All right. So any subarray that consists consists of two parts. I think I mentioned this in the previous slide. The left half is from I to mid, and the right half is from mid plus 1 to j. Okay, right, as shown by this plot again. And the midpoint is the midpoint of the original array. Okay, so we can actually implement this algorithm called find max crossing subarray. We can define this procedure to find the maximum subarray that's cross the midpoint. Okay, let's see how the work is done. Okay, in the next slides, I just copy the code here. All right, so first it takes inputs the original array A and 3 indices, not just low and high, but also the mid. Okay, because we need to use the mid to do the constraints, to constrain that the subarray must cross the midpoint. All right, so the first line of code, it defines a variable to hold the sum found so far for the left side. It's called the left sum. Okay, so it works down from the mid to the low and to examine every subarray in the left half. It's a for loop that iterates from midpoint down to low. Okay, and the sum, so this variable sum is used to do the accumulative addition. Okay, we add all the elements from mid to low to sum, and if this sum is greater than the left sum, then we will mark the current summation and also mark the current index I. Okay, so whenever we have a maximum summation, these are stored in these two variables. And to the right, we'll do the same thing, right? We will use the right summation and the max right variable to mark the maximum summation for the right parts and the corresponding right index. So after these two for loops are done, we will return these indices, the max, the left indices, the right indices, the right index, and the total summation. Okay, the left sum plus right sum, this is the total summation. Okay, so this if we look at how many iterations are executed in the two for loops, it's also a straightforward analysis, because the first for loop iterates from mid to low, then it iterates over that many entries. It's basically half the size of the original one. And the right iterates over high to the mid. It's also half the size of the original inputs. So the total number of inputs is just all the elements in the original inputs in the original array, which is the number n. Okay, so we just it's two separate for loops that covers all the elements in the original inputs. So we can say that if we use a big theta notation, we can claim that it takes big theta of n times. Big theta of n time. Okay. So that is the find max crossing subarray procedure, which solved the third case after we have divided the original inputs. Now let's look at the other cases and try to combine the solutions. Okay. Now let's look at the divide and conquer. The complete solution. Now we are going to implement something called maximum find maximum subarray. Okay, using the previous procedure we have defined. Okay, so this is called find maximum subarray. Now it takes the inputs A with low and high. Okay, if we look at the first 2 lines of code, it basically handles the base case, because when the input has only 1 element, which means the low index equals the high indices, we simply return it, right? We simply return the index here, low, high, and the element itself, because there's no need to compute. And in other cases where there are more than 1 element, then it's the recursive case, and we need to do the divide. How we do the divide is to compute the midpoint. Okay, the midpoint is the low index plus the high index divided by 2 and the rounded to floor. Okay, that's the dividing step. Okay, and now it's the interesting part, because we have recursive calls. First, we need to conquer the left half, because the left half is a smaller instance of the original problem. We can simply conquer it by calling the function itself, by calling a function recursively on the right, on the left part. Note that the input indices is low and mid. Okay, it's the left part. And we do the same thing for the right, conquer the right. Okay, because it's also another smaller instance of the original problem, from mid plus 1 to high. And lastly, we're gonna use the procedure we defined in the previous slide, which is the very smart crossing boundary summation. Okay, we call the find max crossing boundary summation given 3 indices. Okay, because this is no longer a recursive call, it's a new type of question, type of problem, from low to mid to high, and we want to find the maximum subarray that cross the midpoints. Okay, anyway, we need to record the 3 summation, the 3 results. Okay, we need to record the 3 results, and the following if else conditions are simply to compute the which one is larger, which one is, yeah, the line, I think I also noticed the line 12. Someone pointed the let's return. Yeah, so if left sum is bigger than right sum and left sum is greater than cross sum, yeah, I think this need to be fixed. Let me fix it. Okay. Otherwise, it's gonna cause confusion. Yeah, I will upload the code again. Huh. Oh, I fixed the next slide, but I forgot to fix this one. All right, really quick fix here. I think it's done. All right. And share my screen a little bit. Oops. All right. So now it should be correct. Yeah. So after the combine step is done, we will return the whichever one is larger, whichever summation and the indices that have that correspond to maximum subarrays. Okay, so let's oh, it's already the time end of the class, but let me finish this slide. Okay, so we can actually use a recurrence to describe the running time for finding maximum subarray. Okay, so we use some simplified assumption that the input can always be divided by 2. Then, considering the cost for the dividing, which is constant amount of time, and the cost for solving the recursive running time, which is T of n over 2, right? We have 2 subproblems. And then we also need to consider the cost for the solve the non-recursive case, which is to solve the third case, which takes linear time. Because when we analyze the efficiency, it takes in linear time. That's something we already know. All right, and the combining is also easy, doesn't cost us a lot. So altogether, we can write the recursion into the recurrence into this form. If we look at it, it's T of n equals 2 times T of n over 2 plus theta of n, okay, which is exactly the same form as the merge sort, okay. That also means that we will have basically same solutions, which is n times logarithm of n for the finding maximum subarray problem, which is improvements compared to the brute force solution that has quadratic running time. Okay, so yeah, that's how we implement the divide and conquer algorithm for the finding maximum subarray problem. And in the next lecture, next week's lecture, we're gonna go through all the examples, all the methods for solving the recurrences from substitution method to master theorem. Yeah, we're gonna spend some time on those methods. So that's it for today's lecture. And let me see if there's a quiz problems today. Yeah, I think there's a quiz problem for maximum subarray. I will release it later. And also the first assignment is due tomorrow. Yeah, that's correct. Okay. And that's it. If there are any any questions, you can let me know now, or can join the office hour or send me emails.
So for the assignment, can we just submit like a scan of like the problems on a separate sheet of paper? Is that what you're looking for, or?
Yes, yes.
Gotcha.
You can submit on your scan in a Word document or in the PDF file. Yeah, someone has problem accessing the quiz, but the quiz is not a PDF. Actually, it's a question, submittable question on Canvas. I don't know why you have such a case. I actually read your email about it. Let me stop recording now.